So, hello everyone and welcome to our webinar. And in this webinar, we will focus ourselves on parametric design and specifically on using SCIA Engineer with a plugin Koala that is intended for Grasshopper. I will be presenting this webinar. My name is Vladimir, and together with me here is my colleague Jaroslav, who will be answering your questions, whether if you should have any during the webinar. Let's do some quick housekeeping. And we are using the GoToWebinar application. You are muted during the presentation, but I encourage you to use question box in the control of the GoToWebinar to ask questions during the presentation, and we will answer them most likely during the webinar or by email later on. Furthermore, this webinar is recorded and will be posted on our YouTube channel, as is common for our webinars, and so you can see it again or link it to anyone else interested. So let's go and dive straight ahead. So what is parametric design and why to do it? So the parametric design, as we speak about it, is an approach based on some mathematical relationship between number of, or usually quite big number of parameters. It's the modeling itself. It's not done manually in a program, but rather by algorithm, and the shapes of the structure is then defined by functions and things like that. So here we have very simple parametric example of an arc that is composed by 3 parameters: its length, the height, and the number of segments that are used in it. And this parametric design, we have specific goals we want to achieve while designing structures parametrically. In most cases, it's it's modeling of structures that has too many members to be efficiently modeled by hand due to some fancy or non-regular geometry, or we want to have some optimization loop with let's say the finding the maximum load-bearing capacity while keeping the self weight or the material consumption at the same level. There might be multiple criterions, and the parametric shape is optimized based on those. So what parametric design options we have in SCIA Engineer? Just a quick recap. We have a direct parametric modeling available in SCIA Engineer. You can create structure from sets of parameters for basically anything like nodal positions, cross sections, loading, whatever. You can create your own template this way directly in SCIA Engineer, or you can use parametric modeling in Excel, and by means of table input you are quite easily able to import the whole structures in SCIA Engineer to have it calculated and get results. You can use something that is rather new, and that's we called OpenAPI, and you can create parametric model in a programming language environment where we support multiple languages there, and this gives you entire freedom, but it requires some programming skills. And what I will spend most time today on is graphical parametric modeling by means of using Grasshopper as a plugin in Rhinoceros version 6, and a plugin for SCIA Engineer that we call Koala that provides a link between these two programs. If we have a look and start at the beginning, I mentioned we have parametric modeling available in SCIA Engineer directly. Yes, indeed, you can define any parameters. Here I have very simple structure, so I will define, let's say, span and up to be 15 meters, and another parameter that will represent, let's say, half span. And here I can use a formula with parameters that are already defined. When I assign or when I select multiple nodes in the structure, let's say this whole section, I can see that the x coefficient is a number, but I can change this number to be the parameter defined, and in this way I'm able to create structure that is parametric in yeah, here we are talking about topology of the members by means of their end nodes, but we can make parametric height or width of the beam as well, and it can be used even on quite big scale structures where hundreds of parameters are defined and they are linked together, and the structure behaves parametrically in a way that based on the change of the parameters, the shape of the structure is changed accordingly. If I go further, and the second topic that I wanted to show, or the second possibility, is modeling in Excel. Also, I will show it very quickly. You can define some input parameters in Excel sheet, like shape of the floor and number of walls, and each floor can have a certain rotation or certain rotation from the floor underneath. And here in Excel you can calculate basically the coordinates of the nodes. You can create beams by connecting those nodes, and also you can make slabs and walls by connecting those nodes as well. And you can see that yeah, this Excel it supports macros, so you can do quite a thing in there. And when you want to change the structure, you can just change the input parameter. In this case, it's the angle between separate stories. You can Control C and Control V it directly into the table input, and the structure is changed accordingly to the changed position of the nodes. So this is something that is quite readable because it's in Excel. It has its limitations, and if you want to make it more versatile, you need to know programming or scripting in Visual Basic as well. So to offer more freedom, we came up with OpenAPI. An API stands for Application Program Interface, and it's a set of defined functions that we provide in order for anyone to be able to, let's say, launch SCIA Engineer, create structure by their own code in there, run the calculation, and obtain results. This OpenAPI can be used to create complex structures, and whatever you are able to program, you are able to create. And we created it as friendly as possible, given that some programming skills are required, and we provide support for here 5 of the most widespread programming languages, and the methods that are there are quite simple to read through, like create structural node, creates structural node, create beam, creates a beam. Let me show you a quick demo how it works. So I have a code of my own here. I set up some paths to SCIA Engineer, folders, and a project. I create materials and cross sections. I create nodes, slabs, and beams. And at the end, I can refresh the model in SCIA Engineer. I can run calculation, and at the end, I can close the project. So now I opened SCIA Engineer environment. The structure is imported in it based on whatever the code is doing, and it creates 2D elements, 1D elements, and also it runs the calculation at the back side. So after viewing results, you can see that results for this structure is there, and it's parametric, and those parameters are defined in the code or somewhere where the source is coming from. So I can change whatever parameter I want, and I can run it again for a different shape. This is all that I'm going to mention about OpenAPI. We have a webinar that is on our YouTube channel, and it's available for you. It's quite recent. It was done in June this year. So I encourage you, if you have more interest in this, please have a look at this separate webinar regarding the OpenAPI. And now let's go to the main topic of today, and that's the graphical scripting. And it's very similar in general to programming, but you don't write functions, even though you may. But rather than that, you are using mostly predefined functions that you connect with wires. So it creates a very graphical, well, in some cases graphical and friendly to see code then that you can share, or you can directly use to run SCIA Engineer with it, or even to run it on in the background and obtain results and then play with them. There are multiple applications that support such graphical scripting. Today we are going to talk about Grasshopper because Grasshopper we feel is one of the most popular tool used by structure engineers or architects, and it allows creating scripted components. I will get back to that later. And also it has a large variety of native components to create specific things. And I feel that the main benefit of it is the huge community around it. So there are plugins that are made by separate groups of people, and they are very available for anyone to use. And we have a plugin for Grasshopper of our own, and we call it Koala. Let's have a look what Koala is. So I mentioned the Koala is a set of Grasshopper components that allows transfer of the model geometry from Grasshopper or Rhino to SCIA Engineer through XML file, and it can also run SCIA Engineer analysis on the background and output results that can be further used back in the Grasshopper. You can download it at the SCIA garage, or you can just type in a Google Koala SCIA, and the first result will be the one to go for. So what I will show you today, as modeling in Grasshopper is parametric, we will work with some predefined parameters in order to create, let's say, complex 3D truss roof or any structure which looks like this. And these parameters are either quite visual, or they are at the n parameters are the parameters for the number of sections in each direction. So we will today do this. We will also try to do something more of an architectural thing, but also something that can be analyzed by SCIA Engineer, and both these structures actually can be analyzed, and I will show you how that is made in SCIA Engineer. Furthermore, as I mentioned, we can export results from SCIA Engineer, and we can show them in a way that is supported in the Grasshopper back, or we can use it further to, let's say, optimization. And before I start, I would like to get to know you a bit, and I would like to ask you how often are you using Grasshopper or any of those or any similar component, and whether you use them for architectural or structural engineering or bridge purposes, and also whether you are using it like all the time in your daily practice, or whether none at all or not yet, but you would be interested in doing so in the future. So let me close the voting just now, and let's have a look how it went. So we have a portion of people who are using with Grasshopper on a daily basis. That's great. We have some that use it from time to time, but we have quite more than half of people who voted who are actually not using Grasshopper often. So I will react to that, and basically I will I will continue with showing you how things are actually done directly in Rhino. So let me start from the beginning. I mentioned that we have the Koala plugin, and yeah, even you can Google it. And the first entry here is the downloadable page for the Koala. So you can download this zip file and open it right away. Also, as I mentioned, there is a big community of people doing different plugins for Rhino. Those can be found on website Food for Rhino, and we can show you that with those plugins you can do some amazing stuff, more of an architectural way. But I myself have the Parakeet installed myself because it can create some quite generic types of structure. So let's go in Koala right away. And if you download Koala, you will see a screen like this. So there are parametrically predefined different types of structures, and this green box is the Koala. So how does it work? Those are scripts or components that we have that take input that is necessary for SCIA Engineer application or project, and it creates load cases, nodes, beams, surfaces, you name it. There is quite a lot of functions here enabled, and what you need to do is just set up some directories where your SCIA Engineer is installed, where you have some template file, where you want to save the output file, and by this setting up you can just run this script in the SCIA Engineer. So this is the basic examples that you can use to get started with the Grasshopper, and also with having it directly connected in SCIA Engineer. If I close this and I open my own Grasshopper script that I a bit cleaned up, it is if you download Koala, and this is something that we are working on quite currently or quite recent, you are able to obtain the components not as scripted components but as native components in the Grasshopper. So we have multiple here. Some are for creating loads or structure parts, some are for viewing results, and I will be today using multiple of those. So let's get me started. I promised that we are going to create the truss roof structure, and here I have predefined some of the inputs. So I have the length and amount of span, amount of separate sections, and some of the geometric shape enhancers or dimensions in certain directions. I like to work here in vectors, so I basically these sliders with value are very simple to create. You just write a value and a slider is created for you. So that's very basic. The vectors are just converting the value in a vector in a certain direction. So what are we going to start with is actually I will create a boundary curves like this, and I will do that with those vectors. So I need to make curve. Grasshopper work in a way 3. I want to create a 3-point curve. Okay, it doesn't help me, but I can find it in a sorry. Let's just go with curve, and I will show something else to start with. What you can do very simply in Rhino is you can define splines. So you can define splines very simply. Let's say like that. Let me create first spline, then I create a second spline like that, and one more. So I can quickly create splines that are working or that are placed in the zero ground, and I can just by drag and drop I can move one to be quite at the one in the middle to be with certain height. Let me now loft those curves to create a surface. So what I need to do is, let's set multiple curves, 1, 2, 3, and now I have a component that contains these defined curves. I can create a shell just by connecting the curves with the loft function. I will use that later, but now let me actually find the 3-point curve. No, never mind. Sorry, I'm a bit startled now, but it doesn't matter because I can quickly find. Okay, so it's actually arc and not a curve. Sorry for my confusion. So I want to create an arc. Okay. So what is nice about Grasshopper is that you have the direct view here, and if you don't want to see certain parts, you can hide them. I will get back to these later. And when I want to create this curve, I will start with the 0 point. Then the second point, let's say that I'm constructing the curve in a direction of the x-axis. So the second point will be half the span, so I can just take the vector divided by half, and this will be added. I can just add to this vector the vector of height. So the height in x direction is this one. So let me just connect it like this, and I have the second node. What I can do further is I of course need to be exactly clear. I need to add the 0 point here as well. So by double click, I can create a relay here, and I can make a multiple addition. Yeah, at this point, these points are at 0, 0, 0. So it's only, let's say, to be really technical, or technically correct. And the second addition, I again use the 0 point, and to it I can add directly this x vector. So, and here I have my curve created by 3 points. So now when I created a curve, I can actually go further, and I can make the same curve at the end. I will use move functions for it, and I need the curve to be imported in there, and I'm going to also use a vector. I am going to use this one, and it creates a curve at the end, at the next part. So now I need to create curves at the sides, and in order to do that, I basically would like to copy this chunk of or this set of boxes. What I prefer instead is you can create a cluster out of it, let me go one step back, because you can see that this box and this box actually gets the same input. So it's more logical to create a relay and to connect it like this. So this cluster that I'm now creating has only 3 inputs. So I see it takes 0, 0 point, it takes a vector in the longitudinal direction of the arc, and it takes a vector in the vertical direction in the midspan. Now I can just Ctrl+C and Ctrl+V this arc, and I can just change the vectors. So the other one will be in longitudinal direction of y-axis, and it in the midspan it will not use the height in x, but it will use the possible combination of these two vectors. And let me delete these lines, and you can see that this arc is now both its midpoint is offset in both x and z direction. So I have these three curves. I can use quickly the mirror function, so it mirrors this curve, and yeah, and I can also use move. So these functions are always there. You are able just to double click anywhere and write what you want, if you of course know how the functions are named. So this I would like to move in the x direction. So at this point I have 4 curves, and they create together a surface, or I want them to create surface. So I would like to use the edge surface function, which creates surface out of these curves. So let's start with the first one, then second, third. You can see the surface is actually being created, and now the surface is here. Well, surface on its own is a component that can be directly inputted in SCIA Engineer by connecting it to a surfaces function. So it creates a list of nodes readable by the other component, and it creates a list of surfaces. You can see here that the output is in folder Koala, and it's called Koala Truss. I can have a quick look, and here you can see that the Koala Truss was edited a minute ago, so it was created. You can directly open SCIA Engineer, and you can import this XML file by very quickly. Just need to skip this dialog, and we shall see that the surface is being created, and nothing else is actually in the program. I will show later how to do the boundary conditions like surface loads or hinges, but here you can see that right away by just connecting few ties I get a first model in SCIA Engineer. So let's continue with this. So now I would like to create a truss, and I will show it on a simple example. And for that I am going to create, let's say, a curve like this. I will just create a curve component, and I will set this curve to it. What I can further do is I can divide the curve in a number of sections. This amount can be, let's say, taken from this parameter, and it can be like that. So my curve is now divided, and what's the outcome of it is a set of points. So what I can do now is, because the truss is defined, this can be the definition of the bottom chord. If I want to create a top chord, I can actually use this set of points, and I can add them with the height value, and I can't do that right through, because if I'm working with points, they have of course multiple coordinates. So in this case I will create a z vector that I will feed with this value, and it actually creates a vector that is in the correct form, and I can use this vector now. And you can now see that I have a set of points on top and set of points on the bottom. For now I can just select everything else, and I can hide the things I don't want to see at this very point in the preview. So I have two sets of points at this very moment, and what I can do is I can just start connecting them. So I will use Polyline here. Polyline function will actually connect these nodes with Polyline. I would like further in SCIA Engineer to work with this geometry in a way that between each point there is a separate beam element and not this polyline one. So I can just explode this polyline into a specific curves, and you can see that by this measure I created set of 14 curves to be able to use further. So I will Control C and Control V these functions, and this one I will connect to the bottom and this one to the top. Further, I can create a simple line, but not this one, but line with 2 points. So the first point will be from the set of the bottom chord, and the second will be from the top. And you see that as there is the same amount of these in both chords, they are just cleanly connected. I will place this function here. Furthermore, I want to create my diagonals, and how I will do it with a very similar way how when I created this line, but with a simple adjustment. Imagine that here you have the first and second node, so I want to attach the first node in the bottom to the second one on the top. So what I need is I need to from this list of nodes I want to subtract the first one, and from the second list of nodes I want to subtract the last node in order to work with that. So here I can assign index. Indexes here start with 0, not with 1. So by linking the list, you can see that the first point is not highlighted, so it's no longer part of this component. Here, I would like to use the function list length, because the list can be long in the last node I will get from the list length, and I will need to subtract 1, like -1, because the length is from 1, but the indexes are from 0. So let's connect it like this, and you see that that the last point is omitted. Of course, I have to connect it with the second or the upper chord, and now I have two lists of nodes which I can connect simply by a line. And you can see that I have diagonals in one direction. I will just quickly copy these functions, and what I can do is actually just switch these wires. So here there is no wire, so let me disconnect this one, and it's automatically set to 0. So now I have the truss in both directions for this simple curve. Now the truss is, you can see the diagonals are in X shape. If I don't like that, and I would like to have a single diagonal in every section, I can use something that's called curl pattern. And here I just set a few booleans. Let's start with false and true, or it can be also input from somewhere else. I will copy this one here, and I will switch the order like this. Let's commit changes. I fear that I didn't actually commit changes here. So that's something that I need to do. Okay, so commit changes. So now this list can be connected directly to these points, and you see, sorry, Control Z. So you see now that every second point now is selected. So I can actually copy these two, and I can copy them once again, because they already contain the setting. I just change the wire here. I can change the wire to create the line, and you can see, yeah, I flipped it because now every second, but for both. So let me just use this vice versa, and vice versa here. No, sorry. Yeah, the only thing that needs to be done here, I can do it quickly by changing the property. It needs to have the pattern the other way around, and this one as well. Oh, sorry, I'm clicking. And by this, I'm basically let me continue with this. So now what I can do is I can add all these values together. Let me start with the chords and continue with the diagonals. And by this, I will get a list of all the lines, and I will use flatten function just to create a list of lines. I will keep this one away from for now, and I will directly jump back from this simple example to the surface example. Because what I can do with the surface is I can actually divide surface by this function. So you can see that by default it divides it into sets of nodes. Let me just connect it to these two values that I have here for the amount of what you want to see. One remark on the technical side, or on the cleanest of code here in this matter, is that you can see that I'm getting some spaghetti problem here. So I can just click on separate wires and I can hide them, and they will still be there. I can view them by clicking on the component, but they are not bothering me anymore. I will do something a bit different for these. And I will use another entwine to entwine something further. So here you can see that I have a curve that I use, and this curve or these points, this is actually only set of points. So what I need to do is let me fix it for only a bit. Let me create a smaller relay here, and I will connect these elements to the relay. So you can see now that there is only one input is the actual the one input is the bottom chord, and the second input is the top chord. I will do it in a way to be able to reuse this component. So it's always good to if I want to reuse, to make as little connections as possible. And now what I can actually do is that okay, let me also add away those verticals. So now I have here a function that creates everything but the vertical part, and again I can make a cluster out of it, and the cluster is here to be used further. So it requires set of lines as input and set of lines as output of the points. So here I have again the value number of points, and I want to have a second value of points. Let's say in the normals of the surface. So I need to add the points themselves and the vectors multiplied by the actual height of the truss that I want to create. So just like that, and this should work. And now you see that there is another set of points created underneath. If I want to have these actually created in the above the structure, I need to use the negative function, and now I have two sets of points. So I have first set of point here and second here. What my function here does, it actually creates a connection between two sets of points, so I can directly connect it with that, and you can see that the trusses from the defined way were created in a one direction. Let me do the same with the verticals. So the verticals are very simple because they just use the first and the second points, and yeah, and those are the trusses in a one direction. How do I make them in the other one? What I need to do is, if I remember that these are the list of points, and the list of points are just going from this direction, what I need to do, I need to flip them, and I need to flip them both. So let me just connect it to them, and then I can just copy this function, connect it to the new one, and you can see that now I have the truss constructed in all three or both directions as I wanted. What can I now do is, if I have this surface created by the Loft, you remember in the beginning I showed you how to create a surface from just lines. I'm able just to connect this one here, and that's that. There's nothing more to it. So let me entwine these values, and let me work quickly on some boundary conditions. So here I have again quite some members. Let me flatten it so I have only a list of curves, and this can be directly connected to curves here in the beam, in the setup of the beam. What I further need to create beams in SCIA Engineer are cross sections. For the simplicity now in showing you, I will do it quite simply, but for those who want, I can provide quite an finished example that I'm doing now with a bit different approach. So I can basically create a cross section for each type of the beam. I can create the different cross section for truss chords, for diagonals in each direction. It requires a bit more that I don't have time to show now. But if you are interested in this, I am able to provide those that if you leave me your email in the question bar, I will get back to you, and I will send you my finished Grasshopper project. So now what I need to do is I need to combine data. So I need to create a list of cross sections that will have the length of the number of the beams. So I have 1086 beams, and I have 1086 cross sections. Perfect. So let me just connect it here to sections, and the rest what's here are basically layers, prefix of node that they start with n, and some tolerance to find duplicate nodes. So if I have beams, I can go for supports, and to create supports, I need to have list of nodes or list of beams where I want to place those those supports. So the supports I want are actually on curves that are defined right at the beginning. So let me divide this curve at this curve. I don't see it now, but it's in the front and its moved counterpart to the back. So what I want is I want to divide these two curves into points, and in this case I want to have only one only one line between. So I am actually getting four nodes. If I again flatten these values, you can see that here are the coordinates of the nodes that are at the ends of the curves. So yeah, this is exactly what I needed, and I just connect this one to the supported nodes, and you can see that it creates supports at nodes at the correct positions with the naming that was created by creating the beams. We can do actually the same with hinges, because here if I, let's say, I will make now I see that I actually forgot to add the verticals to be able to have them in the SCIA Engineer. So I will connect the verticals as well. And just for demonstration, I know that that I want to create, let's say, hinges on those verticals, and I have 195 of them. So let me create a series here that that will start actually here with one, because the hinges are created on beams, and the first beam and others will be like that. And here I have how many values I need. So let's just connect this one, yeah, and flatten it on the input. So let me just flatten it here, and I need to unflat. So I have here a set that starts with 1, it has 1 between them, and it creates something actually that I don't want. Let me just check. Let me just switch to a project which I actually will be sending you, because here I have it in a bit more organized way, and you can see that how I created hinges here is basically I take the length of the list that is without hinges and the length of the list that is with hinges. I should have at 1 because of the indexing, and it provides a set of indexes as I want them, and it creates hinges on these members with a predefined degrees of freedom and position. You can see that the structure here is basically the same. It is still parametric, so I can let me just adjust it a little bit, so I have a bit less values in SCIA Engineer, and I can go in the Koala folder, and you can see that a truss was created at this, or the XML file was created at this very spot. So let me just open it, and it shouldn't take long to calculate it, and it should also have all the necessary data in there. So this structure, when imported, can be directly calculated, or I can use an approach to calculate them on the background and use the results in the Grasshopper back. So you can see that this structure is with less sections, but it has supports. Let me just magnify them a little bit. So supports were identified at the end corners, and this is all that comes from the Grasshopper. It has the different sections for diagonals, for chords, and it can also have a set of the hinges based on the type. And what I added there as well are loads. Loads are essentially applied the exact same way as hinges. You just specify the beam you want the hinge or the load to act on, and it's applied to it. So let's just run the analysis, and in the background I can get and let's have a look at results, because this will only take a second. And so the results are ready. Let me go to the result service, close all these view flags. I can go, let's say, for the 3D displacement for the load case that I specified, and I can refresh. Let me go now back to Rhino, and let's have a look at some customization, because if you want, this file, as I mentioned, is here to be sent to you. I create one more example that is easy to follow. Let me show how that is done here. So I just hide everything, but I will go with this edge, with this surface. So what I can do is I can use function to populate geometry, or I can by, let's say, random value number of points, and I can use, as I mentioned, different types of plugins. There are ways how to create a, let's say, generic structure around these points. In this case, let me go with just the Voronoi on surface. Voronoi on surface, so it requires sets of points, and it requires a surface, and it creates a pattern with those points in the middle, and the pattern looks like this. This, exactly as this point, is a polygon curve, so I need to explode it into the separate lines, yeah, these lines I need to, because each of this segment has its boundary lines, so all the lines, or most of them, are actually duplicate. So I want in SCIA Engineer to have those duplicate lines removed. So let me flatten the set of lines, and let me just place it here. So here you can see that it was generated 560 lines, but further goes only 301. I can connect these right away to curves, and again, what I can do here, let me go with cross-section 7, and I need to create a number of elements with this cross-section. So I want to use the function to combine data. So I want to have cross-section 7, and I want to have it 300 times. So here I go. Let me connect these two sections, and now when I can go back now to SCIA Engineer, you can see here that that the results are there. They are calculated. So only just for demonstration, let me close this file without any further to be done with it, and I can basically import and open the XML file anew. And in this Koala Truss, now you will see an entirely different structure. Yeah, I will get maybe an error because I defined hinges on beams that aren't there, but I prepared a very similar example for you regarding this one, and on it I will show you how you can work with results. And so we have structure like this. You can see in SCIA Engineer, this structure was imported. It has a cross section that I predefined. It has supports on nodes that were preset, and all the members are loaded here. Now I don't need to use SCIA Engineer anymore. Let's have a look because here the results would be obtained within the SCIA Engineer the exactly same way. But what we have, or what we prepare, and it's not yet available, but it will be in few days time, we have these components for getting results. And here is an example how to use them. But we can use, for example, stresses. So what I can do is I can run the SCIA Engineer file, the project, with this imported structure on the background, and I can obtain results from it. So let me just run it. Or maybe I should have set a bit smaller mesh. Let me close it, or never mind. What I need to do in order not to wait, let's say a minute, let me just put 50 in this slider, or 30. You can see that this directly affects how the structure looks like, and now I can actually calculate it in the background. You see that only command window of SXML application is visible, but the calculation itself is actually being performed on the background. So once the calculation is done, in my result folder here, I will see a result file updated by this structure. So now it's done, and here I show you. You can see that the results of this was created, and I have some internal forces in here, and also some stresses, and this actually has thousands of lines. So let me just connect the result file to here, and you can see I get a vector of the, let's say here in this case, the von Mises stresses. Let me use a curl pattern on them, and I know in this case that the first value is the minimum, and second one is the maximum. So I want only to have the second values. So here I have values for every separate member. And what I can then do is, let's say I can use the pipe function to draw it. So what I want to do is I want to draw the lines. These are the lines. I can draw those lines with pipe, and the pipe can have, let's say, a radius of the stresses. Oh yeah, now it exploded because it's in millimeters. So let me just write divided by 100, and let me connect it like this. So based on the value of the stresses, you will see a different, let's say, in this case, a different value. Or you can even use gradient. You can use gradient, or let me just use this one that I have here already. I can just connect those. I can connect those data to it, and then when I call preview, I can display those pipes with this gradient. So they are now all blue because the maximum value apparently is quite near here. Now it's a bit laggy for me, but as you can change the diameter, you can play also with the colorful settings. Or if I go into to more practical in this, you can actually define an optimization loop that will here take results of the stresses. It will define, or it will investigate if the stresses are smaller or bigger than some limiting value. It can update the cross sections, and it can run in a few loops for you in order to get the cross sections dimensions in a way that they are utilized on limit utilization value. So there is more to come. There is ongoing development, and also these components will be available on the page which I showed you, the Koala SCIA, in few days time. So here I am just finished with the showing, and let me give you some takeaways. What are the takeaways from this webinar? So in the parametric design is actually modeling by algorithms. That's important. We developed the OpenAPI and we have dedicated webinar for it. It can be used for modeling structure and obtaining results, but so can Koala. And now I'm also interested whether you yourself use the how you create your parametric model, if you do, because I'm interested whether you use templates. So if you create a template for specific types of structures, or if you for example receive the parametric model from architect to either analyze it or to optimize it in SCIA Engineer or somewhere else. And I by this last questionnaire, I would like to say thank you for your participation in this webinar. If you have any questions whatsoever, please don't hesitate to ask them. I hope they were answered in the chat, but if weren't, I will get back to you by email, and you can also reach me by email. So no more votes are available. So let me just quickly share with you the outcome. So some of you use templates, and but most of you either don't use parametric modeling or create models from scratch. As I mentioned, I will share with those that want the parametric models or the files created in Grasshopper. And this is all from me. I thank you for your attendance. If you have any questions, reach out for me on email. Follow us on LinkedIn, or follow even me on LinkedIn if you want. There is content posted from time to time. Thank you very much and have a great day.